Okay, I'm actually remaking this video because I made it the first time and then I realized I made it and I didn't want to actually change any settings in the machine, but I saw something I didn't like, so I'm actually going to go through this and actually do it all in real life and run all the programs and actually calibrate everything instead of just showing how to do it all. So this video is going to show you how I set up the Pioneer TTC 200 and the Haimer and a wireless probe. So this method that I'm going to show you is one of many. It's the one that I believe in because it's one I can physically verify. I'm not an expert. This is just how I'm doing it. I'm having pretty good success, and I don't see why you wouldn't either. This method has the link between the tool setter and the work offsets that I think people have a hard time understanding. And the link is the master tool. So it's very important that to use this method, you need a master tool. You can make one. You can, like I've got an ER32 collet holder, and that's a broken carbide 1/4 inch end mill in it, and you can use that as your master tool. Or Meritool sells an actual tool probe calibrator, which is also a great idea. In any event, this is the critical part. This, you'll see later, this master tool, we'll call it, is what will bridge the gap between the Haimer and wireless probes and the tool setter and the machine offset table. So the first thing we need to do is, I guess, just talk quickly about tool length offsets. So in the control, you're going to have an offset table for tools. These numbers are relative to an arbitrary position. So these numbers aren't, one machine to the next. You can't just take this length offset and put it in a different machine and think it's going to measure the same. It's relative to a point on the machine that somebody has to pick. The most common place to pick is the spindle nose. So the lowest point of the spindle, where the tool ends up interfacing to. So that's where I'm going to pick because it makes sense, but it's very important to know that it can be anywhere on the head. If you want it to be relative to here, go for it. If you want it to be relative to here, go for it. This is probably the most common place, but again, I think the important message here is that that location is arbitrary. You can pick wherever you want it to pick. Oh look, I left a screw loose on my way cover. So you can pick anywhere. And I think a lot of people get hung up in this whole process because they don't understand where all the basis for everything is. Like, where's the anchor for all these systems? And I think I'm doing you justice in telling you that it's a random position and you can pick it to be anywhere you want on your machine. But once you pick it, that's the spot. So we're going to use the spindle nose. So that means when we determine a length offset for a tool, it's going to be relative to that position. So what we need to do first is we need to come up with that length number for our master tool. And this is the only time you're ever going to have to use this method, is this initial setup. So we're going to end up zeroing a dial indicator to the bottom of the master tool. Now again, this is a completely arbitrary location in the machine's Z travel. I just picked it here because I know I need enough room to retract Z and get the tool out without bumping the indicator. So, mid-travel, again, arbitrary position. So we're going to zero here now, which I've already done. So as you can see, I've zeroed the bottom of the tool to the indicator. And again, on the indicator, it's just a random spot, but I put Z somewhere and then I jogged the machine, or I put 0 somewhere on the indicator and I jogged the machine until it read 0. Arbitrary, random. Now, Will Bullock who's a great dude who's on forums that I'm on, he pointed out an important point. The end of this end mill is not necessarily flat, and it most certainly is not. So you need to find the lowest protruding spot. So as you can see, if I rotate this tool, there is quite a bit of variation. So this, in this area up here, is roughly the lowest point. Now, there's a lot of like stick slip and all sorts of stuff going on. I don't typically have this trouble when I'm using my Haimer, but giving the head a bit of a bump by hand seems to, you know, let everything settle so you can, you know, pick your 0 point, which I think I actually have to change. This was all supposed to be pre-done, but it's not really working. So we're going to jog. I'm in 1 micron jog. We're just going to jog down a little bit more. And I'm going to bump the head. The bump thing, who knows? Maybe you want to do that, maybe you don't. But for me, it makes sense. So, I mean, I think if I do it again, it's going to be too far, but I'll try. Nope, I'm happy with that. So again, we've now zeroed on the indicator to a totally random spot, and that's all we need to do. We just need to pick a place on the indicator that we're going to repeat to again after this process. So here we are. I've found the lowest point, I believe, and now what we're going to do is set this relative position. So on the Siemens control, we can go into jog, and we can go into relative mode, and this allows us to, if we hit Z0, it allows us to just record this location as a 0, and we're going to measure how far the Z travels when we take this tool out and we 0 again on the spindle nose. It's going to tell us how far we moved, which is going to be our tool length that we're going to use in the table for this master tool. So we're going to, if you're not using a Siemens control and you don't have a relative mode, you could have also just zeroed your work offset, you know, load G54, and then zero this position, and then when you move it and you jog down to the spindle nose, it's just going to tell you you're at a different spot in G54, and you know that's your length. So this is just nice because they've got a method for measuring basically. So now what I'm going to do is I'm going to stop the camera. I'm going to pull the tool out, and I'm going to get set up. I'm not going to move the indicator. This is going to stay exactly where it is, and I'm going to be very careful not to bump it. But I'm going to move the spindle, and I'm going to line it up to a spot that doesn't have holes, and I'm going to 0 it on the indicator, and that's where we'll pick up this video next. Okay, so now we've removed the master tool. I was extremely careful not to bump this in any way. So I jogged up in Z, took the master tool out, jogged back down. You need to move over a little bit in X just to be able to pick up a spot on the spindle in between 2 holes. So I cleaned the bottom of the face and picked it. Again, this is kind of an arbitrary random thing. And I bet if I measured at different spots on this spindle on here, maybe there's going to be some variation. But all that matters is you're picking a point, and you are going to continue using that point. So jog down in Z, 0 the indicator. So again, that's all that mattered. That 0 position we picked at the bottom of the tool is just somewhere for us to come back to when we're touching the bottom of the spindle nose. So now we know that, because this is 0 again, we know that now we've moved down 86.928 millimeters in Z. And I think that's actually super good news. So if we go over to my offset table, we're going to see that, oh, okay, 86,940. So there is a difference. So my master tool, you're going to have to pick somewhere in the table to store your master tool. So I'm using T12 D2. So 86,940. So there is a difference there, and it's interesting to note that that's about the difference that some of my parts have ended up measuring for error. So sometimes when I do an op 1 and I flip the part, do op 2, the overall height of the part isn't exactly right, and this could actually be the cause of it. Is my master tool length might have been slightly incorrect. So now what we want to do, I'm going to record this number. It's always good to do this. Record the number it was before you started. Now if you're just starting from 0, this doesn't matter. So 86,940. 86,940. So I'm just going to make a note of that, just in case I have to come back to that. But the point is, the number that you saw in relative mode is the number you're going to use for the length of that master tool. So 86,928. 86,928. So we're just going to go 86.928. Scroll over. So that's it for that part. Sorry, it's not like we're done. 86,928. 86,928. So what does this mean? This means that we've established a length for the master tool that is relative to a position we picked on the machine, which is the bottom of the spindle nose. Again, could be anywhere. This is a good place to use though. Now, what does this offset table even mean? I mean, everyone knows length offset is the length of the tool, but where this really starts to matter is in your work coordinate system. So this is the tool length offset, but now we also have our work offsets, and our work offsets are how the machine knows where our parts are that we're going to machine. And obviously there's a critical link between the work offset location and the tool length offset. So the machine has what's called a machine coordinate system, and this is we'll call it the absolute location of the machine in its travels, and it's relative to machine 0. So wherever your machine homes at or is zeroed at, this machine has absolute encoders, so it doesn't home. But if we jog the head over here, it's going to be at machine 0. Now the work offset is your offset from machine 0 to your part location, or your work coordinate, your work offset. So that means that, for example, my G54 location is negative 251 millimeters from machine 0. So you have to jog over negative 251 millimeters, and then that is where the work coordinate is telling us to go. Now, in Z, it becomes important to think about the relationship between your Z work coordinate and your tool length offsets. Because as long as you have, I think whatever it is, G43 or whatever, your length offsets active, which of course I can't really imagine ever a time when you wouldn't, there's going to be another offset added to this. So you've got your Z location, which means that right now, if I wanted to go to Z0 and G54, I would jog to the location, and that spot that we had picked is going to be at the G54 location. So this spot on the spindle is what will jog down to Z0. Now, when we load a tool and we activate the tool, for example, right now we have T12D2 active, so this D2 length offset is active, the machine knows the tool is an additional 86 millimeters tall, so the 0 location for our spot is going to be 86 millimeters above where we set the work offset to be. So I mean, this is all like simple basic stuff, but I think it's worth just kind of talking over again in perhaps more plain language, because it's important to realize that all these offsets are adding on to each other, And this is how the whole system works, and we need to understand it, because we're going to manipulate it, and we're going to try and tie everything together so it works properly with no error. So having said all that, this one offset, length offset for your master tool, is going to become critical, and your whole measuring system for everything is going to end up based on this. So now we've established the length of the master tool, and now what we're going to do is we're going to calibrate the TTC 200. And so this, what I'll show, is specific to this, and we're going to use Pioneer's macros and stuff like that. But of course, whatever system you're using, you're going to have a calibration routine. So you're going to load your master tool, and you're going to run the calibration, and what that does is it establishes the machine coordinate location for the trigger point of the probe. So I'm going to get set up to run the actual routine, and then we'll talk a little bit more about that, because there's something important that I think maybe a lot of people don't know, because I see people talking about, you know, perhaps measuring in jog, and we'll talk about why that maybe isn't very good. Okay, so now we've got the master tool back in the spindle. We've positioned it approximately 10 millimeters above the mandrel. Now, we're going to look in the manual. So the manual, the Pioneer manual, describes the process for tool probe length calibration. So this is important because it's going to set the location of the trigger point of the probe. So we can see here that it tells us that this is the format that you use to call it. So L960, that's going to clear all the other variables. R0 equals K. K is the exact length. So that's going to be the length that we established by measuring it with the dial indicator. So it's the same length that's in the offset table. And then that's it. And then L967, it's going to call the actual routine to locate the probe, basically. So you take this, enter it into Machine Data Automatic. So again, and this should be similar for like LNC and whatever the other controller options are. So L960, R0 equals 86.928. That's the length that we used here, right? And then L967, that's the routine that it wants to call to set the location, and M30 ends the program. So we're above it now, we're ready to run. Typically, whenever I'm doing something like this, I'm going to back the feed rate way off. But my recommendation to you is, if you do that, like I do, run it once slow, but then run it again at full speed. Once you know everything's going to work properly. I have verified myself that there's a difference when you run it slow or fast to where the measured location is. So that's for measuring tool lengths. It's also for using a spindle probe. If you mess with the feed rate while you're probing, your location is definitely going to change. So here we are, 30%. I've already run this, so I know everything's okay. But I'm going to hit cycle start, and it's going to come down, and it's going to hit it 2 or 3 times. It's already done it once or twice. This will be the last one. And once it touches, it will be done. It's still going down. Still going. This is going to make the video unnecessarily long. There. Okay. So that was at 30%. So now, like I said, now that we know everything's fine and it behaved the way we expected, I'm going to run it now at 100%. And obviously it's going to go about 3.3 times faster. So once this is done, the location of the trigger point has now been set relative to the length of the master tool. So that's very important. You could, in theory, let's say you wanted to measure it off the spindle nose itself, you would say that the length of the master tool was 0 and actually trigger it on the spindle nose. I mean, in theory that would work as well, but that's not a great idea, and the next step would be impossible if you hadn't done it the way we've done it. So now we've calibrated the location of the trigger point of the TTC 200. We've also established a length for our master tool, and we use that to locate the TTC 200. So this now, we have a link between the machine coordinate system and the trigger point of the TTC 200. The link between those two positions is this master tool. Now what we're going to do is we're going to set up the length of the Haimer, and I'll show you how I do that. We're going to use a gauge block. We're going to put it on the bed. We're going to jog the master tool down beside it, and I can't do it with one hand, so you jog down beside it past the top edge of the block, and you try and slide the block under as you're jogging up until it can pass through. You'll be able to do that all the way down into micron jog, where you'll go up 1 micron and the block will slide through, and you'll go down 1 micron and the block will not slide through. So it's incredibly accurate in my opinion, and this step and this exact step of this process is what gives me confidence in this entire method, is because you can physically feel the location of this block versus the master tool. So we're going to do that right now. So I'm going to do that offline, and I'm going to get it to a position where we know the tip of the master tool is at the exact same height or within 1 micron of this gauge block. So that'll be the next thing we see. Hold on. Okay, so now I've jogged the machine down and I've set the height of the master tool so that the block can slide under it. If I jogged 1 micron down right now, the block would not fully slide through. So this, I am happy to within 1 micron that the current location of the tip of this tool is at the top of this gauge block. Now, offsets. Because we just ran the Pioneer tool probe calibration routine, it went to D0, which means it canceled all length offsets, and that's why we had to enter the length offset manually in the program. So it's very important on the Siemens to notice when it says D0, because that means there is no offset applied. So right now we have T12 D2 in the spindle, however the machine thinks that the tool isn't there. So it can be very dangerous, and I have had at least 1 crash because I didn't catch that the machine had canceled the offsets. And I shouldn't say the machine, it's what it's meant to do, it's just I didn't notice. So now, what we're going to do, if we didn't reapply the offset, then this whole system would be about to fail. So what we'll do is we'll enter T12 D2, and again, we want to be in G54, which it already is, but this is where you would do that. So we're going to hit cycle start. Nothing will happen because the tool is already T12, but now we can see the offsets applied. We'll enter the work coordinate system, and because I ran this once already, and I made this video already once, I was in here messing around. Now the very cool thing to me is I see that it's 0.008 millimeters different from when I just did it. So that makes me very happy that I actually have redone all the steps properly, because that error is probably what I had been noticing in my parts. So this is worthwhile. Doing this video helps me, and maybe it helps some of you. So here we are. We're in G54. This could say anything right now. The fact that it's close is only because I just did this. So what we want to do is in G54, with the tool tip at the same height as the gauge block, we want to 0 it. So we're going to go into measure work, single point, Z, G54, and we're going to hit set work offset. So now G54 believes that its 0 location is on the top of the block. Now, again, tool length offsets and work coordinate offsets. What the machine really thinks is that if we didn't have a tool length offset applied, so let's cancel it for fun. So we're going to go T12 D0. So look at that. Now the machine thinks that the spindle is 86.928 millimeters above the block. So even though we've zeroed it here, right? We zeroed it, but haven't moved the machine. It now believes that this spindle nose is 86 point whatever millimeters above the block. So that just shows you perhaps maybe visually how this length offset business works. And more importantly, what it's showing you is that the work offset is relative to the machine coordinate system. So if we jogged now till it read Z0, that point we measured on the spindle nose would be exactly as high as this gauge block, because that was where we set Z0 to be in G54. So with no length offsets applied, that means the spindle nose is right there. So hopefully these little things that I'm throwing in are helping to paint the picture of how these work coordinate systems operate. Now, what I was just thinking about, actually, it'll mean more for me to talk about when we're doing this with the wireless probe. But right now, we know that G54 is at the top of the block. We know that the master tool is perfectly in line with G54. We're going to jog up, we're going to take this tool out, and we're going to put the Haimer in the spindle. Hold on. Okay, so now, this is one of the most important parts, in my opinion, is we're going to set the length offset for the Haimer. So what I've done is I have installed the Haimer, I've activated its length offset, and I've zeroed it on top of the block. So remember, we set G54Z0 to the top of that block using the master tool. So we're still in G54, and what I've done is in the tool table, the Haimer is T1D2 on mine. I've zeroed it, just got rid of the old number, and you can feel free to do the exact same. So now, when we're in jog on G54, right now with the Haimer zeroed on the block, it's telling us that we're at a Z position of 165.876. So that means the machine knows that the spindle nose is that distance from the top of the block. Well, that is the length offset for the Haimer. So now all we need to do is take this number, 165.876, 165.876, and enter it into the tool table for the Haimer. When we go back to jog, we're going to notice that we are now at Z0. And the Haimer is at Z0. Sorry. And you know what? I'm a little unhappy with that location. Because I'm doing this for real, I'm actually going to slightly adjust that. To me, I feel like I'm a little past. So let's go back up and then come back down. That, I'm happy with that. Let's see. Okay, well, it was where it was. Okay, so now, what have we accomplished? We picked an arbitrary point on the spindle. We measured between that arbitrary point to the end of our master tool. We calibrated the tool setter with the master tool to set its location. we use the master tool to set G54 to the top of this gauge block. Then we loaded the Haimer, zeroed it on the top of the gauge block, and used that measured height with an offset length of 0 to become the new length offset for the Haimer in the 0 position. So now we know that the link between the spindle and the tools has been made. Whenever we measure something with the Haimer, it's going to be exactly relative to the spindle nose when you set the work, and also relative to the spindle nose when you set the tool length. So this, to me, is the critical link, and this is why I prefer this method, is because I can physically verify the connection between the Haimer and the master tool. So the next thing we want to do now is we want to set up the length offset for the wireless probe. And so I'm going to quickly get set up for that, and I'm actually going to use the Pioneer macros to do that, because I think that's what most people are using, is the Pioneer probe, and so I'll show how those macros work. And I like the Pioneer macros, so I'll do that right now, and I'll get set up and we'll go over it. Okay, so now we've loaded the wireless probe into the spindle. I have jogged down to about 10 millimeters above that gauge block. Actually, I'm just going to lower it down just a little bit more. Just to be within for sure, just so we know it's going to work. So what we're going to do is we're going to get the probe to measure the block, and I'll explain how that's going to work. We're going to use the macro to measure NZ, and the macro is going to output to G55. And we're going to compare G55 to G54. So I've copied them so they're the same. Now, in reality, if the length offset of the probe is correct, when we measure the top of the block in G55, the number is going to match. But since it's going to be a little bit different, we're going to have a difference between the two numbers, and we're going to be able to use that to tweak our length offset. So you are going to, I guess what we'll do, just for fun here, is we're going to make this a length of 0, and we're going to really go for it. So 122,941, I'm just going to record that, 122,941. So that was the old length of the probe, 122,941. My probe is in T1D1, which I'd recommend for you as well. So we're going to change that to 0. So now that we set that to 0, when we're looking at the output of G55, we'll have the exact number to use to calculate the length offset of the probe. And that number is going to be the difference between G54 and G55. So in order to do this single point measurement, we can look in the Pioneer manual, and they talk, this section is to do with single point measurement. So without getting too far into it, if we look at the example here, which starts up here, what's important? Well, we want to activate length compensation, which we will have. This is going to reset all the R variables, very important. Then this will matter if you actually have the Pioneer probe. You'll want to run this L9023 to start the probe. We don't need it. We're also already in position, so we can skip all this middle stuff, which is very confusing. And this is the line that's going to matter. So R1 equals -100, so that's actually trying to probe in X. Since we want to probe in Y, we're going to say R3 equals -10. So that's going to probe in incremental mode -10 millimeters in X. So it's going to go down 10 millimeters. Then R5 equals 1. Well, we're actually going to do R5 equals 2, because this is the output for the work offset. So right now this would set G54, which we don't want to do. So we'll go R5 equals 2, which is G55. Then this is the actual program to run, so L9012. We'll do the measuring. And then if you have the Pioneer probe again, L9024 will shut the probe down, and M30 is to end the program. So in machine data automatic, 9008, clear the variables. R3 equals -10, so that's R3 is Z, or Z. -10 is how far to go. R5 equals 2, that'll write to G55. And then L9012 is the actual program for measuring, and M30 is program end. So again, we're gonna back this right off, and because it's the Drutronics probe, I'm just gonna give it a wiggle to start. And I'm going to be watching the control screen when we do this, but I'm going to hit cycle start, and we're going to make sure that this does what it's supposed to do. Now, you notice it's going up. Now it says probe fail. So why'd that happen? The reason why that happened is because we are not in incremental mode. We are in absolute mode. So when we said go to -10, what it was trying to do was go to the basically the machine coordinate system location of -10, which is only 10 millimeters below top of Z. So that is an important thing to know. And I'm going to give you a tiny little tip for the Siemens control, because you don't have to switch to incremental mode. In fact, I've never done it, and I'd have to look up how to do it. It's obviously a G code, but you can do this still in absolute mode. You just have to kind of be smart about it. You're trying to give the macro a target location, and there's a way to have that be variable. So you could create your own little sub-program that will basically always probe 10 millimeters below where you have it set. So it could be a really quick way to probe various locations. And I'm going to show you how to do that. I'm just going to pull up the code that I need to use and get it pre-programmed in here so that you're not watching me do that. Okay, so this tip will be Siemens related only, unfortunately. So the different controls have what are called system variables. So they're variables inside the control where you store critical system information. So in this case, you know, what we had was R3 equals -10. We were trying to say, hey, go down 10 millimeters. But in reality, what was happening is it was interpreting that as go to Z -10, as in the absolute position -10 millimeters. Now, what I didn't show happening the first time is that the probe is always on G59. So it's important to know that when you're running the Pioneer probe, G59 must be 0 across the board. G59 is going to equal your machine coordinate system. So when we go back to this, now that we know that, hey, hold on, let's make a call to G59 before we set some of these variables, and then we can do some tricky stuff. So we know that when you call L9012, it's going to switch to G59, but we're going to do it first so that we can extract some information. So we've moved the probe to where we want to be in order to start probing within about 10 millimeters above the surface. So what we want to do is, instead of R3 equals -10, we're going to say R3 equals, and then this $AA_IWZ. What that is the system variable for the exact current location of the work coordinate system in Z. And then we're going to say take that number and subtract 10 from it. So no matter where you are in Z, it will go 10 millimeters lower than where you currently are. Now, if we wanted to, so that's why the call to G59 before that is very important. because it's saying IW is the work coordinate system. I believe, since we know that G59 is equal to the machine coordinate system, you could probably also call AA_IMZ, which is the current machine coordinate system. And in fact, no matter what, that actually kind of maybe makes more sense. But this works, it's safe. Call G59, call this code, say subtract -10 from it, or subtract 10 from it, and then target work offset is G55, and run the program. And of course M30 is still down here too. So now let's run this and see what happens. So trigger the probe on. I'll try and zoom in. So I'm going to have my finger on the trigger here. I'm going to run it first slowly. So as you can see, it came down for the first touch. Everything's normal. There, and it's done. So it's successfully completed, no alarms. Now we're going to run it at full speed, so 100% feed rate. So we'll run it again. Okay, so now it's done. So now what are we going to expect to see in the offset table? Sometimes for me, it's important to try and think about your expected outcome before you look at what the outcome was. So whenever I'm experimenting or, you know, measuring something, or I'm trying to figure something out, it's important to think about it before you look at the output, you know, come up with like a hypothesis. So what I'd expect to see is in the offset table, the G55 is obviously going to be different from G54, but the difference should be, you know, over 100 millimeters basically. It's going to be, hopefully what it's going to be is the length of our probe. So let's go into the offset table. So here we go. So yeah, G54, remember we use the master tool to set it to the top of the block, is -467, and G55 is now -510 point whatever. So this will now be the interesting thing. I need to use my phone to calculate this. So I'm going to take I'm just going to go 510.0783 minus 467.374, and that difference, that number, I'm going to stick it here in the length offset for the probe. So that's what I'm going to do. I'm going to put the phone down because I need to use it, and set that all up, and then we're going to measure again and see what happens. Okay, so I did the math, and it was only like 40 millimeters difference, and that made me realize I made a mistake. So what I did is I still had the length offset applied for the Haimer. So there you go. There's a mistake that you can make to screw all this up. So again, think about what you expect. I knew to expect a number over 100, and when I calculated at 40, I knew that something wasn't right. So I switched it to T1D1, repeated the process, and now when we go back to the offset table, we can see that it's a number that's over 100. And that's exactly what I was expecting. So now I'm going to take the difference from these and apply it to the offset table. Stand by. Okay, so now what I've done is I've basically said 467 point whatever minus 344 point whatever equals 123.1727. So I went over to my tool list and I entered that number into the length. Now, I'm sure there's a system variable for this, but my machine is set to round on the microns column, and that might not sound like it's annoying, but it actually is. So sometimes I have trouble. Probably what's going to happen is when we go to measure, it's not going to completely equal 0. There's going to be some amount, like within 5 microns maybe, difference. So don't be surprised. Unlike the Haimer, this isn't going to let me probably get right to 0. So anyway, we've taken the difference now from the Z locations, added it to the tool list to the length offset. Now we're going to go back. We're still on T1D1, which is good. We're going to go back into machine.automatic, And we're actually just going to run this program without changing anything. So I'll flick the probe on. And now we're going to hit cycle start again. And then we're going to see what happens. So it's measuring. Now we're going to go back in. And again, what I'd expect to see is that the Z offsets for 54 and 55 are going to be very similar. So here we go. So now G55 is negative 467.3712. So remember, because of that rounding, it's got a difference of basically 3 microns. And if I try to adjust this, so what, in theory, what you could do now is you could now do the same math, except now you're coming up with a difference to add or subtract from the length offset. But I know from experience that I'll be chasing my tail because it's rounding on the tool list. So this, within 3 microns, I am pretty happy with that. I don't know what that is in tenths, but I'm going to say it's probably less than a tenth, which obviously is pretty darn good. I'll do some investigating. I'm pretty sure I can set this to be 4 decimal places, and then I can make this even more accurate. But this is the way it is right now, and this was the result I expected. And now I know that the probe will measure to within 3 microns of the Haimer, and all of that is relative again to that master tool. We'll use the master tool to set the work offset to the top of the block, and then we calibrated the Haimer and the probe to match that location, that work offset. We made sure that we can replicate it using the Haimer and the wireless probe to get there. So again, all of this is now relative. All these lengths and numbers are all relative to that spot we picked, that arbitrary spot on the bottom of the spindle nose. So now, because this machine has absolute encoders, and I'm sure that non-absolute encoder machines are susceptible to this as well, but when I crash the machine, even nothing too serious, what happens is that encoder position changes ever so slightly. So after a crash, you're probably going to want to reset the locations of things. Now the really cool thing is, if I crash now, all I have to do is put the master tool back in the spindle, put it over top of the probe or the tool setter, and run that length calibration routine again, the tool probe Z calibration, and then instantly all of the tool lengths are still valid, the probe lengths are still valid, and any future tools that we measure using the tool setter will also be correct and relative to all the old ones. So that master tool would prevent you from having to remeasure all your tools after a Z shift, like due to a crash, which happens. And like I said, it doesn't even have to be a very bad crash to have that change. So I guess I'm kind of done with what I hoped to demonstrate in this video, and I hope that this helps kind of clear the air a little bit about the relationship between machine coordinate system, work offsets, length offsets, and how to properly set up all these tools so that everything plays nicely with each other and they're all based on the same reference point of the machine, which is the critical part. So there you go. If there's anything that you guys would have liked me to cover that I missed or that I just kind of breezed over, you can kind of let me know. You can make a comment or whatever, and then maybe I can do a supplemental video or at least explain it in the comments or the video description. So if I missed anything, let me know, and I hope you found this useful. Alright, talk to you later. Bye.